Okay, let's get started again. So welcome back to the last session of today. So this will be on the AFLOW materials database and machine learning, so AFLOW-ML. So here we're going to be discussing some machine learning methods that have been developed and trained on AFLOW data and which are now available through an AFLOW, both through an online application on the website, as well as through various application programming interfaces so that you can programmatically incorporate them into your materials design workflows. So just to again introduce these concepts. So we saw in the previous session with Dr. Esther's, so tools like AFLOWML and the REST API provide a great way to download and wrangle data, so you can search the actual database of materials that have been calculated with density functional theory. The problem is that the DFT generally is quite computationally expensive, even though we've managed to calculate something like 3.5 million materials with AFLOW. If you remember back to the very first session, so the introductory session, where we showed that there was something like 10 to the power of 177 different possible materials hypothetical materials that could be generated using the AFLOW prototype library. So if you were to take all the prototype library that Dr. David Hicks was showing on Tuesday, if you were to decorate all these possible prototypes with all the different possible combinations of elements, you would have something like 10 to the power of 177 hypothetical materials. Now, this is way beyond, orders of magnitude beyond what we can calculate with density functional theory. So therefore, the idea is to use some of this data that's already been calculated from first principles to now train machine learning models that we can then use to accelerate the materials discovery process. Okay, so what we did was, so for the main machine learning model that we're going to be discussing today, so this so-called PLMF machine learning model, and I'll discuss what that stands for in a few minutes. But first of all, what we did was at the time, we had something like 26,674 unique materials in the ICSD part of the AFLOW database. So this is the one where we're focusing on materials properties rather than on whether or not the materials exist or not. So these are materials that are already known to exist. And we use the data for these materials on aflow.org to train a gradient boosting decision trees machine learning model. So the predictions are based on structural morphology and on elemental properties. So the way we characterize the structural morphology is using a Voronoi tessellation to generate a crystal graph. So the way it works is like this. So first you build a Voronoi cell around each atom. So the Voronoi cell, you build this by taking each pair of atoms, you look at the distance between them, you find the midpoint between the two atoms. At that point, you create a plane that's perpendicular to this line joining the two atoms. So then for each pair of atoms, you form these cells. You form these set of planes. These set of planes will then surround each atom. So they form the Voronoi cell of this atom. And in this way, using this what was called a Voronoi tessellation, you can divide up the space of the material into a series of Voronoi cells. So then that's the first step. Then the next step is that this then allows you to determine which atoms are bonded. So basically, you consider the two atoms that share a face, like here. So if the two Voronoi cells of these two atoms share a face, then these two atoms are considered to be connected. So it's like a way of determining which atoms are bonded. So if these atoms are connected like this, then you can, by connecting up all the atoms in this way, you can form a crystal graph. So then these connected atoms form what we call structure fragment descriptors. So the nodes of this crystal graph are the atoms. Edges on this crystal graph correspond to bonds. And then you can build up path fragments. So these sort of linear fragments of different lengths. You can also build up circular fragments and different types of polyhedrons. So in this way, you create these sort of subsets of the graph, these little fragments of the graph, and these are essentially the descriptors that we use for our model. Okay, then what we do is we take these structure fragments and we decorate them with elemental properties. So things like electronegativity, ionization potential, covalent radii, and so a number of valence electrons, position in the periodic table, these sorts of ideas. All these types of different elemental properties of the atoms. We decorate elemental properties. We decorate the nodes, so that these different atoms, the atomic species. with these properties, and this is what forms then these property labeled materials fragments. And this is what how we built what's called a feature vector, which is the input to the machine learning model. And this is how we characterize the material. So how we tell them the machine learning model what type of material we have. So for this PLMF model, then with this structure fragment descriptor input and with calculated data as being the sort of the target features. So things like the electronic band gap and thermomechanical properties, things like bulk modulus, shear modulus, the by temperature, and so on. So we train the machine learning model. So there's two different sets of machine learning models. One was for electronic properties and the other is for thermomechanical properties. Then within the electronic properties, the first thing that it does is that there's a classification model to determine whether or not the material has a band gap. So whether it's a metal or an insulator. So if it's a metal, then there's no band gap. If it's an insulator, then there's a regression model that's used to predict the value of the band gap. Then the thermomechanical properties, these are just regression models. So it predicts things like, again, like the bulk modulus, shear modulus, and so on. So these sort of properties that were calculated using the AEL and AGL methods that I described earlier. So at the time we actually trained this model, we had maybe about half as many properties as we do now. So we had maybe about 300 of these properties. 3,000 of these properties. What was interesting is that between the time when the paper was originally submitted and the time when we were doing the second submission after the the revised submission after the referee reports, we had calculated maybe an extra 700 of these properties, of these material, 700, the properties, thermomechanical properties for initial 700 materials. And if anything, what we found was that this actually improved the predictions of the model. So that in other words, that even when we added the extra materials that weren't in the original training set, the model still held up. So it was actually pretty reliable. And this is something that we were pretty happy about. So once again, we can do once we have this model trained, we can do various things with it. One of the things we can look at is partial dependence of the properties on the different input descriptors. So this can tell you a little bit about how the machine learning model is getting to these values that it predicts. It can tell you it can also be useful for identifying trends and understanding what's going on inside the materials, you might be able to discover new design rules using this kind of analysis. So on the left here, we see that the bulk modulus, so this is the change in the bulk, so this is essentially the difference in the bulk modulus of a particular material from the average value of all the materials is on this y-axis, while on the x-axis is the volume per atom of the material. And you can see that generally speaking, that there's a pretty strong dependence of the bulk modulus on the volume per atom. Basically, the smaller the atom, the smaller the volume per atom, so the more tighter packed the atoms are, the higher the bulk modulus will be. And this is something that's already quite well known. It's something that's kind of expected and it makes intuitive sense. On the right-hand side, this is something we don't really understand yet. It's something we're still sort of thinking about a little bit. We're not sure if it's a real effect or maybe it might be also an artifact of the way the training data was generated. So this here are the two different, the lattice constants in different directions. So what you can see here is that if the lattice constants are similar, so along this line here, then you have a strongly isotropic cell. Whereas if the lattice constants are very different, so for example, up here or down here, then you have a highly anisotropic cell. So a cell where the length of the cell in one direction is much, much larger than the length of the cell in the other direction. And what you can see here is that there seems to be quite a strong dependence of the Debye temperature on the anisotropy of the cell. So if you have a cell that's very long in the C direction, but relatively short in the B direction, so along here, say, we tend to have a much higher Debye temperature. So again, this is something that might be an artifact. It's something we don't really understand exactly why this is happening. And but it gives you an idea of the kind of unexpected things that machine learning models can throw out. And then you have to try and investigate whether they are a real effect, whether it's an artifact, or what you might even discover some kind of new underlying design rule and new underlying correlation in materials from this kind of analysis. We can also investigate how well the machine learning model actually does. So here we compare for the bulk modulus, the shear modulus, and the Debye temperature. So here on the vertical axis here, we have the prediction from the machine learning model. On this axis here, we have the experimental data. So this is the actual experimentally measured value. And along this axis is the calculated value that's in our AFLOW database. That's actually the data that was used to actually train the model. And here you can see that all three tend to agree quite well. So because in this case, the calculations are reasonably accurate prediction of the experimental values, this means also that because the predictions are relatively reliable compared to the training data, that means that because the training data is also reliable, it means that they're also relatively reliable to the actual experimental values. And you can see these R squared. So this is the essentially the correlation is quite high. It's of the order of 0.99 for the bulk and shear modulus, and of the order of 0.97 for the Debye temperature. So you can see there's a bit more of a spread on the Debye temperature than there is for the bulk and shear moduli. Okay, so that's a background to one of the models, and the main model we're interested in, this PLMF model. And now we're going to talk a bit more about how you can actually access this model, especially through the online interface. So the model here, it's available at aflow.org. So if you go to the main aflow.org page, you will find the AFLOW-ML model here in the top right corner. And you can also go directly to aflow.org/aflow-ml. So if we go to this page, we see something that looks like this. Here we have three different models. So we have the PLMF model, which is the model I've been discussing so far. We have what's called another model, what's called a molar fragment descriptor model. So this is a different model. It's trained, it has less, it doesn't have the same kind of structural information as the PLMF model. And it primarily focuses on just on the composition of the material. And this is mainly trained on experimental data to predict vibrational energies and entropies. Finally, we have the AFLOW superconductor model. Again, this is a model that's trained to predict superconductivity. So basically the superconducting critical temperature. Again, this model doesn't incorporate structural information. It's just trained this time again on the compositional data. So going back to the PLMF model, because it requires structural information, you need to give it the structural information in some format. I think it can handle a few different formats now. So here we have the POSCAR file, so the vast POSCAR format. You can also see it can also handle the quantum espresso structural input. So once you copy in your POSCAR file into the box here, you can then hit run prediction. It will take a few seconds, depending on the material, to make the prediction. And then at the end, it will give you a prediction as to whether the material is a metal or an insulator. If it's a insulator, it'll predict the band gap. Then it makes a prediction of the energy per cell. And then it predicts things like bulk modulus, shear modulus, the heat capacity, the Debye temperature, thermal expansion, and so on. So before we do the exercises, I'll just give a quick demonstration example. So, okay. So we go to the AFLOW-ML page. Like I said, here we have a polar property labeled the PLMF model, the molar fragment descriptor or MFD model, or the AFLOW superconductor model. And here's where we put in the POSCAR file to get to give the data. So for the molar fragment descriptor, it also takes a POSCAR file as the input, while the AFLOW superconductor just takes the composition, so just takes the chemical formula. Okay, so let's go and work through an example. So if we go to search for structures, so we can search, if we go to this is for the Encyclopedia of Crystal Prototypes. So this is what Dr. Hicks was discussing on Tuesday. So we can use this to generate POSCARs that we can use as input for a machine learning model. So for example, if we take the cubic space groups, and then we go down and we search for, we go down, we get the rock salt space group, which is here, this one here. It's time to go into, so then we want to generate a VASP output. So we're going to select MG and O. For this one, we can use 4.05 as the lattice constant, because that's lattice, more or less the experimental lattice constant of magnesium oxide. Then we hit VASP output. Okay, so then we get our POSCAR file. We can then take this POSCAR file, copy it, paste it, and then paste it into our input box. And then we can hit run prediction. Okay, so now it's running. So it takes a few seconds and then the results come up. So here we get it's an insulator. Band gap is 3.6 electron volts. The energy per cell. We have bulk modulus, shear modulus, different heat capacities per cell and per atom, by temperature, and thermal expansion. And then here, because there's a few questions about it earlier, there's also some data on the calculation details that were used in the model to train for this particular material. In particular, we have, this is the what we call the KPPRA, so K points per reciprocal atom. So this gives you an idea of the K point grid density that was used. And then below this, we have if there was which PBE pseudo version of the PAW pseudo potentials were used, and then if there was any U value. So if there's a U value for a specific U value was used in the calculation. So maybe something we can try doing is, instead of doing magnesium, we can try doing nickel in the same structure. So now we have nickel. We'll keep the same lattice constant for now. If we put this in instead, we can run the prediction. Okay, you can see now what the prediction is running. So it's being submitted to our server. And machine learning model is running, and here you get the predictions. And now for the calculation details, you can see because this is a D block element, now we have a U value that's being used. So here the U value is 5.1 electron volts. Okay, so that's how the online interface works. Before I go through the exercises, does anybody have any questions so far? If you can just put them in the chat. Otherwise, I'll just run through the exercises before we go to our breakout rooms. Okay. So this time it says to use the, okay. Okay, so there's a question. Okay, there are two questions in the chat. First is, just to be sure, is the ML model pre-trained? I'm not sure I perfectly understand. So yes, you're correct. The models are models that have already been trained on AFLOW data. So we're not training the model on the fly. So you can't really upload your own data and retrain the model, because training the model actually takes several weeks. What you actually get out then are what you're actually using is predictions from this pre-trained model. So you can upload a new structure, and then it can, based on the model itself, it can give you a prediction of the properties based on the existing pre-trained models. So then the next is to give an example of quantum espresso. So I don't think I've actually tried this before, so let's see. But here, if we press the QE output, so let's hope this works. So now we get the QE format, quantum espresso format. So let me copy, paste. I think now it's actually been set up, so it's actually been developed and being revamped a little bit since the last time I did this, since I actually made the slides. But it looks like we've actually revamped it, and I think we now automatically detect the format. So let's see what happens. Let's see if it works. We run the prediction. And let's see if it recognizes the format. And if it gives the same results. So here we go. And you see that we get pretty much exactly the same results, whether we use the VAS POSCAR input file or the Quantum Espresso input file. Okay. So are there any other questions? Otherwise, I'll start going through the exercises. Okay, so the first exercise is to use the prototype library application to generate a POSCAR file, or if you want to generate another file format, it's like a Quantum Espresso file, based on the Heusler prototype, decorated with elements of your choice. So then you should copy the structure into the AFLOW-ML application and run the PLMF model, and then see if it's a metal or an insulator, and what are the values of the bulk and shear moduli. Bulk and shear moduli. So there's a question about the references of the ML model. So yeah, I can add this into the chat once I've gone through the exercises. Or maybe if Dr. Rose is there, maybe you can add the PLMF paper reference to the. So we actually have, it's actually this paper here. And so this one here is just this Nature Communications. And Corey's going to add the DOI in the chat. Yeah, and then as Dr. Esther points out, you can also use the AFLOX API to download AFLOW data and then try and train your own model using this data as well. But this is a lot more involved, and it's not something we're going to try and do training machine learning models is not something we're going to try and do an exercise on. Okay, so then the next one is the third exercise is to run the MFD model for the same structure and see what properties this model gives. And finally, if you want to upload the chemical formula for this material to the AFLOW-ML application and run the ASC model. So the want to see what the superconducting critical temperature is for this composition. Okay, so if nobody has any other questions, I think we should start assigning people to breakout rooms and head into the breakout rooms. And then let's see now. It's now around 1926 here. So if we come back here around 1940 German time, so about 20 to 8. Yeah, you're welcome. Okay, so let's head back into the breakout room and come back in about, let's say, 14 minutes or so. Okay, so what is the average time to train the PLMF model on these 26K materials to be trained on HPC machines? I don't think it was trained on HPC machines, but I think it was trained like on a specialist server. I think it was of the because they trained it iteratively, it took a few weeks, if I remember correctly. I don't know if Dr. Rosas remembers. He might have been working more closely with the people the guy who was actually training the model. But I think it was of the order of 2 to 3 weeks to train the model, or to train, let's say, a version of the model.
No, the model took I think a day or two. We asked him to train it a few different times. So we saw that it took a day or two of training overnight with certain GPU. I mean, it depends on your GPU setup, right? So if you have some nice power with GPUs, which is obvious, that's a problem today in today's world. But if you have nice GPUs, then you can train the model pretty quickly.
But I think, yeah, because they trained it a few times, they trained it iteratively, it generally took maybe about 2 weeks to actually get like a proper converged version of the model. I remember right. Okay, so I think, was there another question?
Yeah, I had another question in the breakout room, whether or not these the ASC transition temperatures are for type 1 superconductors.
So this is an interesting question because, okay, so if I remember correctly, I think Dr. Roses was more directly involved in this work than I was. There's they trained one model, but they actually found that the model itself broke into 3 or 4 different models. So the model itself was able to tell that somehow cup rates were different than conventional superconductors and were different from the iron-based superconductors. So the model itself actually, they trained one machine learning model, but the machine learning model itself was able to learn that there was actually different types of superconductivity. So internally, it actually developed itself multiple different models, if that makes sense. And so, yeah, if you read the paper that's linked, so let me share my screen. So for the ASC predictions, is it possible to apply external pressure? In this case, no, because all you're doing here is for the let me pull it up here. So the ASC model is you're only supplying the chemical composition. So now, okay, so I'm guessing the reason you're asking about this is because there's quite a lot of recent work done on especially high pressure hydride phases. So things like the lanthanum hydride, I think it is, but there was the hydrogen sulfide phases. So again, for these things, there's a few things going on. There's the first of all, at high pressure, so it's highly compressed, and that changes the density of states. The second thing is that you get new phases when you go to high pressure. So for both of those things, the information will not be incorporated. I don't think there was any of these new high temperature hydride, like hydrogen-rich materials used in training this model. So I'm not sure how well the model actually works for these kind of more recent high temperature superconducting materials. Okay, so let me share my screen again. And okay, and let's go through these exercises. Okay. Okay, so the first one is to use the AFLOW prototype library to generate a POSCAR file based on the Heusler prototype and decorate it with elements of your choice. And then to copy the structure into the AFLOW-ML application and run the PLMF model, and then check if it's a metal or an insulator, and what are the values of the bulk and shear moduli. Okay, so we go to our AFLOW page, we go to our prototype encyclopedia, then we can search by space group, or we can type in Heusler. So we have different options, and we want to get the normal Heusler structure. So you can either use the default elements, or you can maybe change one of these elements. So in this case, let's change the CU to CO. And select the VASP output. Here we're just going to keep the same lattice constant, but that's another thing you can do. You can play around with this lattice constant and start seeing how this affects the properties, at least from the PLF model. Then we can copy this. And then let's open another one of these. So then we take the AFLOW-ML page, we open that up, and we put in the new POSCAR file. And then we click run prediction. Okay, and here we can see that this prediction is for a metal, so it doesn't have a band gap. And here you can see the different properties. And if you scroll down further, and this was a question that came up earlier, was about the U values. You can see that this is trained, because this is trained on data from the ICSD part of the AFLOW database. It's trained, some of the entries have the DFT plus U corrections, so you can get the U values as well. As well as that, you can also get information about the pseudopotentials used and the K-point grid used in the training set. So this gives you an idea of at least how reliable the underlying DFT data that was used as the training set would be. And then one question that actually came up inside the breakout room I was in was, there was a material somebody tried that actually ended up, that they happened to know was a semiconductor, and this predicted it was a metal. And again, we should emphasize here that because this is trained on DFT data, DFT is actually quite reliable for things like bulk and shear modulus, And that's why I was showing, as I showed in the picture where we're comparing the calculations and the experiments and the predictions. DFT does, of course, tend to underestimate the band gap, so that the predictions of this model do actually tend to underestimate the band gap somewhat. They get the trend pretty good, but they actually predict what the DFT band gap will be very well, but they're not predicting. But the problem is that the training data, the DFT itself, tends to overestimate the band gap somewhat, even with due corrections. Okay, so that's the PLMF model. If I copy this again, if we go to the Molar fragment descriptor, and we put the same thing again, and we hit run prediction. And here we can see heat capacity, vibrational free energy, vibrational entropy properties that it uses, that it predicts. And then finally, we want to go to the ASC. Let's go AL, CO2, NN. So here you can see that this is not a superconductor. So here we have basically, the model makes two different predictions, one with a cutoff of 5 Kelvin and the other with a cutoff for 10 Kelvin, for where it's actually considered to be a superconductor. And in both cases, it's below voltage D, so this is basically not a superconductor. So now if we just go and reset this, and we use the default, this IBCO cup rate phase, and hit run prediction. And let's see if it actually gives you a prediction for this material. So this one is taking some time to run, actually. So I think so one other thing to mention as well. So I didn't really mention it during the previous one, is that when we do this PLMF model, so this predicts that this material is a metal, and this is more or less what you would expect, because for something with aluminum, cobalt, and manganese. And this is probably one of the weak points of machine learning models, is they tend not to give you anything too unexpected. So the really weird materials, so machine learning models are very good at interpolation. They're not so good at extrapolation. So they're really, really strange. So they're never really going to predict anything that's outside the bounds of the training set. So like, for example, if you're predicting a bulk modulus, they're never going to predict a higher bulk modulus than any value that's already in the training set. And that's why the predictions tend to go with, let's say, more conventional wisdom than something unexpected. So that's also why sometimes you get, it does miss some of the more interesting materials as well. Okay, here's the here's the prediction that's given by the model for the superconducting model for this IBCO material, and here you can see it's around 90 Kelvin or so. Okay, so let's move on to the second part of the talk. So this is another question that came up inside the breakout room I was in, which is whether this is being done. These are sort of things that are already pre-learned inside the browser, or whether it's a lookup table, or whether we're actually running the model in real time. So this is actually, so the answer is that this online application will actually submit this structure to the machine learning model that's inside our that's on our server. The server will then run the machine learning model to make a prediction, and then give you back the predicted values. So we wanted to make this available through an application programming interface, so something that people could actually incorporate into materials design workflows. So to do this, we wanted to we wanted to do in such a way that we could basically, instead of having to everybody have to install the model themselves, we wanted to have some kind of a centralized database, and where we could update the model and so on. So that, and we wanted to make it programmatic. So we wanted to create this programmable interface to make it accessible, programmatically accessible. So the models are now programmatically accessible by this AFLOW-ML API. So the idea here is you take, again, a postcard file, so the structure file, you post it to an endpoint. I'll show you a bit more detail what this looks like. This gives you, once you get Hardness Prediction, this gives you back a task object. So that's a JSON file with a task ID. Then you basically, and it's sort of a task ID and sort of a prediction URL. So basically another URL you can query that you can then retrieve what's called a status object. And the status object, it will either tell you whether we'll have one of the entries in the status object. Again, it's another JSON file, will be something called success. So if it's successful, then it gives you back your prediction. If it's not successful, then it might tell you something like pending or failure. If it's failure, it might, so there's something wrong. Maybe your input file isn't formatted properly or something like this. Or it's pending, in which case you basically just have to query again until it's finished. So if it's pending, it basically means that it's inside a queue that's queued up and you're waiting on the prediction. In addition to this, we've also developed a Python client. So this is something that's really written in Python that you can install and then allows you to really incorporate this model into workflows. So if you're interested in doing that, you can go and download this model from our webpage. I think it's just, let me see. I think it's actually from the source page you have to look at. So if you go to source, save the source code. So yeah, I'm not quite sure now where you actually go to download this Python client. But we're not going to be spending too much time on that today, so we're not going to worry about that for today. It's not really necessary, but it's something that some people might find interesting. So let's keep going. Okay, so here I'm going to give an example of where it was used. So if you read this paper here, this NPJ computational materials, basically what we did was we integrated this AFLOW-ML API. So to use this to integrate the PLMF model with this genetic algorithm called AFLOW-ML to discover new super hard carbon phases. So the idea here is we use predictions of the shear modulus from this machine learning code to estimate the hardness, and we use this model from Toher, so from this MRS bulletin, where you basically just you can show that at least for harder materials, the hardness tends to correlate quite well just directly with the shear modulus. There's more sophisticated models out there that also involve the bulk modulus. However, we found that actually the simpler model was actually a bit more robust, especially when it came to incorporating with these genetic algorithms, because what was happening is that instead of actually optimizing the hardness, it was trying to minimize the bulk modulus and gave some very unphysical structures. So instead, we decided to use this simpler model. So then what the genetic algorithm does is it takes different known structures. So in this case, this is the carbon diamond structure. This is what's called the Lonsdaleite structure, which is sort of a hexagonal analog of diamond structure. It then combines them in different ways to form new structures. And then it then assigns a fitness criterion. In this case, we combine the hardness and the energy to simultaneously try and optimize mechanical properties and thermodynamic stability. So here we have the hardness. We try and find a material with the highest hardness, and with the lowest energy. And then we assign some weight. In this case, it's just 0.5. So we equally weight hardness and thermodynamic stability. Then based on these probabilities, this then in the next iteration will tell you whether or not these structures will be used as the new input structures to form additional structures. Okay, so then here you can see some of the predictions. In particular, this structure at the top right, so there's carbon diamond using this model estimates a hardness of around 75.6 gigapascal, to put things in perspective, while this one is actually estimated to be slightly harder than diamond. So, and this one you can see is sort of from this tiling, so this green and white, green and yellow tiling is indicate lanceolite type structures, while the blue tiling indicates carbon type structures. And so you can see that this is sort of a mixture of carbon and lanceolite type structures. And this is, so this material we expect to be possibly even slightly harder than diamond. Okay, so now to go into the details of how the model actually works step by step. So what we do is we submit a vast POSCAR to the prediction endpoint with this curl command. So we can, so this prediction endpoint is just at aflow.org/API/aflow-ML/PLMF/prediction. Then we have this data URL encode, which basically tells it to encode this POSCAR file as into the right format to submit by a URL. Then it retrieves this task object, which is this JSON file, and this JSON file will contain this results endpoint. So we append this to this AFLOW-ML endpoint. So here now we form a new endpoint that we query to retrieve the results object, which is aflow.org/API/aflow-ML/prediction/result, and then this task ID. So this task ID will be a unique ID that's assigned to each submission, so that then you can query that ID and retrieve the results for that prediction anytime in the future. And that in principle should be stored indefinitely. Yeah, so you can see here's the ID, and then you use the same ID again to retrieve the results. And then once you get this results object, here you have the status. And in this case, the status is success. So that means that it was predicted successfully. Sometimes you'll get a status of pending or failure. So this tells you the job is completed. You have, then it gives you a prediction. So for things like bulk modulus, Dubai temperature, heat capacity, and so on. Electronic band gap, metal or insulator, etc. And it also tells you the specific model that's being used. So let me just do a demonstration. Okay, so I have a POSCAR file here. Again, this is from magnesium oxide. I can see URL. And then I have to go to http://aflow.org API AFLOW-ML. AFLOW-ML PLMF prediction. Prediction. -- data dash URL encode. Equals code and file at POSCAR. One second.
Cormac.
Yeah.
Yeah, I had already saw that you missing an API after work.
Bye. Yeah. There's something else missing. The API is in the wrong place. 1 second. Okay. So as you can see, typing this in by hand is quite tedious. Now it works. Okay, so now we get our prediction endpoint. Sorry, our task ID. So now we grab this prediction. Enter. And now we get our retrieve our results. So here we can see our prediction, bulk modulus, shear modulus, heat capacity, and so on. So this is basically how it works. You submit your POSCAR file, you get your task ID, then you use that to formulate the results area URL, which you can then query to get your prediction. So as you saw, that's a little bit cumbersome. And quite awkward to do, and very easy to make a mistake. So you wouldn't want to do this, especially if you have a lot of files that you want to submit. You wouldn't want to be trying to submit this by hand. So a much, much better way to do this, and this is what we generally do, is to use a Python script. So you write the Python script once, and then you can use it to submit different files. And I'll go through this, and then I'll show you the script. So it should already be uploaded to your to the virtual machines, just to be inside your directories. So I'll go through it. So first, one of the important things we do is we import this sleep library. So this allows us to pause, to wait a few seconds between requests. So to give it the prediction, to give the model some time to actually make the prediction, especially if there's a lot of tasks submitted at the same time. I might have to sit in the queue for a few minutes. Then we have the AFLOW-ML server. So aflow.org is the server. The API is this as API/AFLOW-ML. The model we're using here is PLMF. So you can also set this to, say, MFD. Then we encode the POSCAR. So here it's assuming that the POSCAR file is just named POSCAR, so you can change the name, or else you can change the name of the file here inside the script to point to make sure it's the same match of whatever is the name of the file you're using. Then you can retrieve the task object, extract the task ID and the results endpoint. So here we retrieve the task object, we then extract it. So we extract the task ID. So then we formulate this results endpoint by adding up the server, the API, and the results endpoint. Get the results URL. Then we basically query this results URL and we check the status. So if it's pending, it'll sleep for 10 seconds and then requery. If it has started, it'll also sleep. So this is the model is actually currently in the process of making the prediction. It'll also sleep for 10 seconds and then wait. If there's a failure, it'll write out the error prediction failure. So that might mean that just say, for example, might be something either wrong with your script, or that maybe you typed MDF instead of MFD, or there might be something wrong with your input file. It might not be formatted correctly. And finally, if it's successful, it'll actually print out the JSON file that you receive. Okay. Okay, before we go to the exercises, let me just show you where these files are. So if you look inside here, as I mentioned, we have this AFLOW_ML_API. So we can open up this file and we basically see it's exactly the same as the one we were looking at before on the slides. So you've got your server, your model, you encode your POSCAR file, then you build your results endpoint, results URL, and then you basically loop over until you get a successful prediction, or else it writes an error message and a failure. Okay, with that, we're going to take a look at some of the exercises. Okay, so the first exercise is to copy this Heuser postcard from the previous exercise, so the one that you generated online, or else you can generate a postcard using the AFLOW proto command, if you remember how to use this. So you can generate a new postcard file and copy it to this directory, or generate it in this directory using AFLOW, and then modify the AFLOW-ML API script to print whether the material is a metal or an insulator, and then if it's an insulator, to print the band gap. So basically, you should take this results JSON and you should extract the relevant information from it. Then modify the script to run the MFD model for the same structure and see what results are returned. Then finally, you can use AFLUX or the AFLOW.org advanced search page to find the entry for the MOTI alloy system with the lowest formation entropy per atom. Then download the relaxed structure and use the AFLOW-ML API to find the bulk and shear moduli for this material. Okay, so then if we want to go into breakout rooms and these different parts, there's a lot of different parts to this. So let's take, and we still have some time left before we, in this session. So let's come back at, I think it will be 21:30, no, 20:30. Is that right? Yeah. So 8:30 p.m. German time. So about 17 minutes from now. So if we want to go into our breakout rooms, we can go ahead and go now. So the first exercise was to copy the Heuser structure from the postcard from the previous exercise to the directory, and then modify the script to print whether the material is a metal or an insulator, and if it is an insulator, to print the band gap. Okay, so what we can do here is, where's this one? So we can either copy and paste in from the online.
Can you share your screen?
Sorry. Share screen. Okay. Yeah, so we can either copy and paste in the postcard from the online prototype engine, or we can also use AFLOW in the command line to generate a new prototype from scratch. So we can go here, we can use the AFLOW proto command. So this is the Heuser prototype command. So AFProto equals A B2C underscore CF16 underscore 225 underscore A underscore B C underscore B colon, and then I'm going to decorate with aluminum, cobalt, and magnesium. And then I'm going to key this into a postcard. Type this into a postcard. So here it prints out the resulting postcard file. You can also see now there's a new file called postcard in the directory. Okay. So now let me change this back to PLMF. Okay. And let's print out the results. So here it will run. Okay. And now we can modify the file itself. So let's open this up and get it. And then we can append, so something, if it's success, we can append something if we can add if results underscore JSON. So this is our JSON file, and then we have the keyword. So the keyword is the type, whether it's a metal or an insulator. ML should be square brackets. ML underscore egap underscore type is insulator. Print material is insulating and gap equals when we do results underscore JSON. So this is the advantage of using JSON in conjunction with Python, is that it very naturally reads else and then print. It's very easy to incorporate in it's very easy. So basically a JSON file converts very easy into a Python dictionary. So you can incorporate the data from the JSON file into your workflow, into a Python-based workflow. Material is metallic.
Cormac, you're missing a colon in the in line 42.
Yeah, if
Print takes parentheses, not brackets, in 45.
yes. There we go. Okay, so save.
And on 43, you forgot to close the bracket.
Let's see. So let's see the error. That's the fun part. Okay. So it's telling us on the next line, but that's because this was line 43. Yeah, this bracket isn't closed. But actually, it's the previous one. Equals. Actually, it should be here. Okay. Now it's running. So now you can see it submitted the prediction. It's waiting for the result. And now it prints out that the material is metallic, so there's no band gap. But if there was a band gap, then it would print out the value of the band gap. Okay. So the next one is to modify the script to run the MFD model. So let's open this up again. So this time we're here. What was it? MFD. And here we can just print out the full JSON file. So now you can see it runs the MFD prediction and looks for the job completion. Okay, so then the final exercise was to use the either use AFLOX or the advanced search page to find the entry in the MOTI alloy system with the lowest formation entropy per atom, download the relaxed structure, and use the AFLOW-ML API to find the bulk and shear moduli. So here, I'm just going to use the online page. So, okay. For some reason, the page is returning things in a strange order. But here's the one with the lowest formation entropy. So if we open up this page, we can also find the concar file, and then we can copy and paste this into our virtual machine, or else we just copy and paste it into the ML page as well. But you can imagine if you want to loop over the entire alloy system and find not just this bulk just for one material, but the bulk modules for everything in that alloy system, then it would be much easier to write an AFLOW script and incorporate pipe the AFLOW script into the AFLOW-ML API. And that's how you would do it in that case. Here we go. So we copy it into the clipboard. So then let's open up another gedit window. Copy and paste. Let's hit the gedit. Type copy. Okay, gedit is giving me trouble again this time. Let me try VI. Okay. So here. Okay, so now we've saved a new file called postcard.moti. So we can edit our script to point to this postcard instead. So here we want to do the PLMF model. And here we want to point to postcard.moti. Let's save it. Let's run. And then let's wait for the prediction. Okay, so now we get it back. And if we look through here, we can see our bulk modulus, our shear modulus, and so on. Okay, so that's the last of the exercises. So unless anybody has any other questions, I think we can start wrap up for today. And I'll just hang around for a few minutes, just in case anybody has any additional questions or anything else they want to know.